in fact, we certainly don't expect anything to break unless some random part fails, and that we will eventually will have to turn things off just because the power is not enough. Ed Stone, Chief Scientist for the Voyager missions.
Helen, I saw your face mirrored mine actually during that recording. Do you think anyone will ever hear that record? Oh, that was like...
No, it's a wonderful idea. I was just thinking about it. Because you get into this more, I mean, obviously that's 70s technology, but a lot of the technology we're using now, this idea that, the human lifespan versus the lifespan of this technology. And I always kind of want it to be the case that he's got a son who takes over his job, and then it goes on generation after generation, and then eventually one of his daughter, that's incredibly sexist. It's shaming myself. Or, he's hit and one at some point in the future, one of his descendants gets this method. That would be wonderful. But yeah, I think it's maybe not most likely thing.
Inspirational, David?
Oh, I think so, very much so. And particularly Ed Stone, I think it's wonderful to hear his voice, just as James Van Allen in the late 50s with the first American satellite gave us such profound information about the magnetosphere and how the Earth interacts with space. Ed Stone's done that to the whole solar system with the boundary of the heliosphere.
Well, thank you very much to our guest, David Baker, author of the Haynes Owner's Workshop Manual for the International Space Station, and Helen Keane, whose Spectacular show will be playing at London's Leicester Square Theatre on January the 27th. The Space Boffins podcast is supported by the Atrium Space Insurance Consortium and is a Boffin Media production in partnership with the Naked Scientists. I'm Richard Hollingham.
And I'm Sue Nelson. You can follow us on Facebook and Twitter, where we'll put some pictures from today's podcast. We're back in a month, but we'll leave you with some highlights from that Voyager golden record on its way to the stars. A list of these sounds can be found on our Space Boffins Facebook page. Let's see if you can work them out for yourself. Thanks for listening.
Hello from the children of planet Earth.
Selamat malam hadirin sekalian, selamat berpindah dan sampai bertemu lagi di lain waktu.
Or DIY investment options. It's never been easier to start investing. Search investing in the CommBank app.
What did you say?
Investing carries risk. Consider the T's and C's and PDS where applicable, and fees and charges before deciding. From professionally designed or DIY investment options, it's never been easier to start investing. Search investing in the CommBank
Not
app.
affiliated yet.
Investing carries risk. Consider the T's
I
and
don't
C's and
stream
PDS
often
where
enough
applicable,
or
and
for
fees
long
and
enough.
charges before deciding.
Are you ready to begin?
Yes, I'm all set, Gareth. Any program about science or a scientist today is almost bound to focus on space.
Hello, welcome to a packed end-of-year Space Boffins podcast with Richard Hollingham and Sue Nelson.
In partnership with Naked Scientists. This time we have a guided tour of the International Space Station, an interview with the Chief Scientist of Voyager missions, as well as the 10th man on the moon. 10 Republican credits, and you can guess what he's talking about here.
I would not consider a one-way trip. Buzz Aldrin would do it. He's already told me he'd like to go that far. Why would you stay?
More from Apollo 16 astronaut Charlie Duke and a potential holiday destination later.
Our studio guests are space journalist and former NASA scientist and engineer David Baker, who makes a welcome return to the podcast, this time as author of the Haynes Owner's Workshop Manual for the International Space Station. And we're also joined by the writer and performer of Radio 4's It Is Rocket Science, described as a low-budget, highly subjective look at the history. It's on the way to... Well, news...
Is he getting inspirational, David?
Oh, I think so, very much so. And particularly Ed Stone, I think it's wonderful to hear his voice, just as James Van Allen in the late 50s with the first American satellite gave us such profound information about the magnetosphere and how the Earth interacts with space. Ed Stone's done that to the whole solar system with the boundary of the heliosphere.
Well, thank you very much to our guest, David Baker, author of the Haynes Owner's Workshop Manual for the International Space Station, and Helen Keane, whose Spectacular show will be playing at London's Leicester Square Theatre on January the 27th. The Space Boffins podcast is supported by the... The Space Boffins podcast is supported by the Atrium Space Insurance Consortium and is a Boffin Media production in partnership with the Naked Scientists. I'm Richard Hollingham.
And I'm Sue Nelson. You can follow us on Facebook and Twitter, where we'll put some pictures from today's podcast. We're back in a month, but we'll leave you with some highlights from that Voyager golden record on its way to the stars. Most of these sounds can be found on our Space Boffins Facebook page. See if you can work that out yourself. Thanks for listening.
Hello from the children of planet Earth.
Selamat malam hadirin sekalian, selamat berpindah dan sampai bertemu lagi di lain waktu.
From professionally designed or DIY investment options, it's never been easier to start investing. Search investing in the CommBank app. Investing carries risk. Consider the T's and C's and PDS where applicable, and fees and charges before deciding. From professionally designed or DIY investment options, it's never been easier to start investing. Search investing in the Combank app. Investing carries risk. Consider the T's and C's and PDS where applicable, and fees and charges before deciding.
Thrusting space science into the audio dimension. This is Naked Astronomy.
Of space debris, and what will we learn from LOFAR? This edition of the Naked Astronomy podcast comes from the RAL Space Conference at the STFC's Rutherford Appleton Laboratories. We'll explore the crossover between space science and medicine, catch up with curiosity, and find out how a new satellite helps to test the latest tech. I'm Ben Valsler, and this is Naked Astronomy.
Supported by the STFC, this is Naked Astronomy. For more information, look us up online at nakedscientist.com/astronomy.
Alright. Hopefully we're back now. Oops.
Of course, one's always got to be aware of anomalies. So how do you know this isn't one?
Well, to a large extent, we don't. You're quite right, we need to be aware of anomalies. But it fits into a pattern that we've been seeing, a picture that we've been building up of these sources over the last 10 years or so when we've had the satellites in orbit to view them properly. What we think for many of these ultra-luminous X-ray sources now is they are sources that are accreting material. They're feeding extremely rapidly at around this Eddington limit. And in fact, we think that actually many of them are somehow managing to feed above higher than this Eddington limit, this supposed natural ceiling to how bright they can get. So it's interesting to us because this verse fits into that picture where we're looking at something that's accreting at about the Eddington limit and it's behaving in a way that we've seen other sources in the galaxy do. So it's helping us continue to build up this picture and fitting in with our ideas.
Tim Roberts from Durham University, speaking with Chris Smith. The Rail Space Conference is an annual event held at the STFC's Rutherford Appleton Labs in Oxfordshire. Each year, staff at Rail Space and invited guests discuss the developments in space science and technology, as well as some of the issues that space scientists face. The last 12 months has seen numerous developments, but one of the most significant was the successful deployment of the Curiosity rover, part of the Mars Science Laboratory mission. Dubbed 7 Minutes of Terror, the landing of the rover employed a novel sky crane platform that lowered the rover to the ground whilst holding itself aloft on rockets. Rob Manning, chief engineer on the Mars Science Laboratory project, was one of this year's invited guests and explained how he came to be involved in the program.
Well, for me, it was a natural because I've been involved from the Mars program really since its rejuvenation after it came out of hibernation, in fact, for nearly 20 years, with the start being a Mars Pathfinder in the early 1990s. And from there, as chief engineer for Mars Pathfinder, that same core crowd went on to develop the Mars Exploration Rover. So it was natural for me to continue that on my efforts with the Mars Science Laboratory.
The Curiosity rover has been unique. It's bigger than anything we've ever put out before. It's got more science instruments, it's doing different things. But what do you think have been the sort of key breakthrough moments or the key developments starting from those early 90s rovers that have led to us being here today?
Every mission, both from an engineering and science perspective, has provided a foundation for what Curiosity has become. Curiosity represents by far the most complex vehicle we've ever put in outer space. But we could not have done it without these other missions and all these other experiences. Certainly one of the things when you do something new and different, and there's much new in Curiosity, that it's a very different rover than Mars Exploration rovers, the Spirit and Opportunity rovers. Its power supply is different, its thermal architecture is vastly different, its science capabilities are vastly superior. But the real hard thing for us with MSL is figuring out how to glue all these pieces together and get them, in some sense, fit together and work together. And that has been the challenge.
So what's been the driver behind it? Has it been NASA engineers who said, well, this is what we need to put on our new rover? Or has it been the scientists saying, these are the answers that I'm seeking, therefore you need to take this sort of instrument?
It's done together. The scientists really told us long ago that, listen, we would love to see more little rovers, roving geologists, but if you think about it, what we really need next to satisfy first day of Mars is geochemistry. And it was clear from the very beginning that to produce the kind of laboratory science we want to do on board the rover, we would have to put laboratories on board, which means the rover is bigger. The question is how much bigger. And we knew it had to be significantly bigger than Mars Exploration Rover, which we had somewhere under 20 kilograms of scientific equipment on board. We were trying to get something 5 times that much for this vehicle. And so just that effort forced us into whole new modalities of how to get to Mars. So knowing what the scientists ultimately wanted, not certain exactly what they wanted before, we knew we had to have sample analysis capability. We need to be able to extract material from the surface, either through cores or drills or whatever, or scoops or whatever. So we were able to work in parallel while the scientific community made up its mind about specifically what it needed to do. And particularly much of the science was selected, virtually all the science was selected via announcements of opportunity that were sent out to the scientific community from NASA. They were competitively selected instruments. But we all knew what was coming. We knew that those kinds of capabilities were out there and people were using them. And this is what people wanted to do. So we had to build a rover that ultimately could get us there and do this. So it was a joint effort, really.
And so was it then the pressure to put this bigger rover out that led to the engineering decisions that led to this incredible sky crane and the incredible landing mechanism?
Well, in many respects, we knew about the limitations of all the landing systems we had developed over the years, going back to Viking, but also including Mars Polar Lander, Pathfinder, and Spirit and Opportunity, which were actually in development, actually barely started. In fact, the idea to lower the rover and land it on its wheels, ropes, predates the invention of Spirit and Opportunity. That was done basically in February 2000, when the first idea came along. We discarded the idea right away. This idea actually even goes back even earlier. I mean, in many respects, many systems used rockets and ropes combination going back to even the Soviet Mars lander, which used solid rockets, which we adopted. Many of those ideas for Pathfinder. And so the idea of converting it into a liquid propulsion system and being very in controlling the velocity with precision dates to about that time. But we had to think about it. We ended up really spending about 3 to 4 years mulling that idea over and trying to understand the physics better. knowing full well that if you go in this direction, we'd have a lot of explaining to do, because Buck Rogers told us this is how you do it. And so this is how you land on another planet. You put a rocket below you, and you land, and you climb down a ladder, and then you plant your flag. That's how you get to another planet. So when you turn upside down and put the rocket above you, which lowers you down on ropes, and then have your rocket fly over and crash, that was a very awkward story to tell. But we had both the experienced people from Apollo, Viking, and helicopter pilots to all give us feedback on this idea. And gradually we realized this was the way to deliver a 900 kilogram rover to another planet. And so all of us were very comfortable. This is the way to go. We just had to prove it to others, and we did.
And of course, it was a phenomenal success. Does that mean that future rover missions are likely to employ the same sorts of technology?
I think it improves the probability that will happen.
And what do you see as being the next step? It seems very early, given that we're only just starting to get scientific answers out of curiosity, but what's going to be the next thing that we do as Mars?
We haven't made up our mind. I mean, I think that there's two things. One is we need to give curiosity time to discover and answer the pile of questions that we have about Mars. And certainly about the pile of questions about Gale Crater and Mount Sharp. But we also know that the scientific community has made it quite clear. We have something we put together called the Gale Survey. Every 10 years, the scientific community gets together and says, this is what we'd like to do. And one of the things they want to do is they want to go to Mars themselves. Because despite the improved quality in in situ science, in situ laboratories, the laboratories back here on Earth are still massive and bigger and improving all the time. So scientists would love to be able to bring even a half a kilogram of carefully selected core samples from rocks on Mars and bring them back to Earth. So that pathway has not been abandoned, and I think it's on the path eventually. It's not going to happen for now, but it will happen.
And finally, I would be insulted if I didn't ask somebody from the Curiosity mission about all of the recent, let's say, hype about what was actually found that was suggesting it may have been organic molecules. What's the real story there?
Well, the real story is our enthusiasm about the whole mission got confused with enthusiasm for this particular set of measurements, which are really preliminary. I mean, we would never have expected to measure organics, for example. And the reason for that is because Mars, it does not filter ultraviolet light from the sun like our ozone layer does here on Earth. So you expect the organics to be broken down. We wouldn't expect to see more organics. What we saw was a fascinating amount of chemistry. In fact, rather complex chemistry. And we're still trying to make heads or tails of that now. And that's what we're very excited about. Unfortunately, when people see scientists being excited, they assume it's something new. Unfortunately, that message did not get clearly communicated. Yet we're still excited. And the possibility of eventually seeing even more complex chemistry. When we actually go into Mars, and particularly as we get closer to Mount Sharp, where we see these layered terrains, and we see embedded rock structures, if we're lucky, we have to be lucky to drill into the part of Mars that may have had the organic chemistry and environmental conditions that would allow life to exist.
That looks a bit better.
But that's still in the future.
Rob Manning, Chief Engineer on the Mars Science Laboratory project. Conferences foster discussion and can lead to interdisciplinary relationships. And it was perhaps with this in mind that the organisers invited Kevin Fong. He's a medical doctor and the director of the Centre for Space Medicine at University College London. And he was invited to talk about the interface of space and medicine.
We've been doing human space exploration now for over half a century, and I think the thing that we've learned from that and the wider and older program of unmanned space exploration is how to work across disciplines in very highly complex areas, large, complicated data sets. And so I think it's really the ethos of working in that way that we could bring to medicine to try and make some disruptive changes.
We've already seen some very nice technological examples where, for example, people are using the software that interprets MRI scans in order to interpret deep space images. So there are technological crossovers, but it seems that the gist of what you were saying earlier was that it's more about our willingness to go beyond our current boundaries and to explore. And that seems to have some very strong knock-on effects in how we understand and help to protect the human body.
Certainly, I think we're of an age where we spent many, many years going deep into narrower and narrower subspecialities. I think it's really fruitful. But now is a time when we've got to recognise that there's at least as much, if not more, to be gained by going across those disciplines and work together. Now, that's not easy to do because everyone these days is a super specialist, but I think there are real prizes there. I also think that we often set up this false dichotomy between exploration, particularly human space exploration, but space exploration in general, and what is the practical realities of the world, the economy, the health problems, etc. It's really fair. When you look back at medicine, there was a great statement that someone at the Welcome said to me recently, which was that with medicine, we're very good at superimposing this false narrative of progress. You know, like a Blue Peter ticker tape timeline of one bit of advance followed by another and all the way to great glory. Well, actually, when you look at it in detail, there's this haphazard leaping from one thing to another, creating almost as many problems as you solve along the way. It has the feel of exploration and really looking for what it is. And if you can accept that medicine in the 20th century, and indeed has been as exploratory as any other area of science, then I think the importance of exploration in medicine is that medicine is exploration. And in exploration in that sense has always been our future and our survival.
Practical problems you mentioned. There is a lot to talk about the future ideal of sending manned missions to Mars. And presumably we need to develop as much of our understanding of how the human body responds to long periods in space, as much of that as we do the actual technology that will get us there.
So this theme of creating technology that we wrap around ourselves to protect ourselves, but then realizing that those same advances in technology also have exposed us to different risks, is what has made the 20th century what it is. It's what's changed our concept of survival in the last 10 short decades since Scott's expedition to now. We're going to get to Mars at some point. I think that's a given. Before we can do that, before we can look out for places to explore, we've got to look in at ourselves and understand ourselves better. So there's this lovely thing that you see in what the Industrial Revolution and technology have done for us, which is allow us to create these sort of cocoons of protection around ourselves, which allow us to extend in exploration, but they've also forced us to look within into ourselves. And so at the same time that they've enabled us to look out and have ambitions to go further, they've also enabled us to look within and try and better understand ourselves. And so I think that's the great beauty of the exploration of our age. It goes in both directions. And at the end of the day, that's the goal of all exploration, that you hope that you return after all of your travelling, having a better understanding of yourself.
And so now, how do you want to see, or have you hoped to see, people working together to try and make sure that we do look in both directions and achieve both the very long distance exploration and the internal exploration?
So I think that you've got to be able to do the both things. I think you've got to be able to do the basic curiosity-driven research, the thing that always has been science. And I think you've got to allow that and foster it, because that is the bedrock, really, of the sorts of skills that you need to do the more interesting things, but perhaps the things that look more like innovation, that look to government like the attractive things that you get out of science, which is making widgets that allow you to heal people better or make a bigger profit. I think that what you've got to do at the moment is shore up your basic curiosity-driven research, but find a way of superimposing on top of that a system whereby you can move across those disciplines, find the synergies between them, find ways to make those synergies work as innovations both in healthcare and for the betterment of the economy. And I do think it's an exciting time, and I think if you get it right, everybody wins, right? You get better basic science, and you get a more productive economy. You can't be absolute about this. You can't say, well, you've got to give me an unlimited amount of cash to go and find curiosity. You live in the real world. But the opposite is just as bad, which is trying to turn science into some sort of R&D wing whose only purpose is to try and generate jobs and create profit, because whatever that is, however successful it turns out to be, it won't be science. That's not what science is.
Kevin Fong, who, in addition to his medical roles, is a Wellcome Trust Public Engagement Fellow and Director at UCL's Centre for Space Medicine. This is Naked Astronomy with me, Ben Pulsler. Still to come, we'll find out what can be done about space junk, and we'll discover how LOFAR fills a gap in our observational horizons. But first, how do you test technology in space? Finding a launch partner and then designing and building a satellite is prohibitively expensive. So much of the technology that gets used in satellites is already very well established. Testing new tech, therefore, is tricky. To get around some of these problems, Surrey Satellite Technology has developed Tech DemoSat. And to find out more, I spoke to project manager Victoria O'Donovan.
Tech DemoSat 1, it stands for Technology Demonstration Satellite, and it's a satellite designed to act as an in-orbit testbed for new UK technology. So it's essentially a small satellite, it's about a metre cubed, and it houses about 50 kilograms worth of payload on it, so all sorts of experiments and instruments from all over the UK space industry.
Why do we need something like this? Surely people have tested their own satellites and their own kits before. Why do we need to bring it together in one?
The idea is, when you have a new piece of equipment, or you have an instrument, customers are very reluctant to fly it. Obviously, when they're paying millions of pounds for a satellite, they don't want to take the chance on something that hasn't been tested, that hasn't been flown, and it hasn't got what you call in-flight heritage. So this is a bed where we can put lots of those new equipments on, we can fly them in space, we can test them, we can check their limits, we can give them that in-flight heritage so that when they go forward and try and sell them on the market, it's proven technologies that customers will take a chance on.
And using the word customers, again, I think of these sorts of things as being for academics, where we're learning about technology or we're using technology to ask science questions. Does this mean that actually Tech DemoSat is for a broader audience than that?
Certainly, it is for a broader audience. It's for academia, so there's certainly some academia experiments on there, but it's also for industry as well. So for the likes of people like Surrey, when we have our customer that we try and put our new technology on board, they are reluctant. So we want to try some of our new commercial things. So it really is a mixture between industry and academia.
If I wanted to test some technology, let's say I have a new bit of communications kit and I want to know if it works in space, how would I go about getting it on Tech DemoSat?
Okay, so obviously for future Tech DemoSats, the way it would work, the way it worked on Tech DemoSat 1 is we basically put a call out to the UK industry. We asked them to tell us a little bit about the technology, the sort of size it was, the volume, the data that it took, what they needed to do with it. We put a few stipulations on how it would need to sort of interact with our bus, so to speak. There was a number of submissions put forward, and then they would then gone through by an independent party, and they sort of selected the most appropriate, and we fit as many on as we can.
It sounds very similar to the CubeSat idea, which is where you have these common parts or these common interfaces that enable you to test lots of things in one go. Does that mean that we've had to sort of standardise the technology in order to be able to do this?
Unfortunately, we had to go with a standardised device because the basis of the programme was that it was low cost and it was rapid access to space. It would be possible to put different interfaces on it, but you would be adding complication, you would be adding time. So in order to meet the objectives, we had to be fairly strict and say everybody conforms to the same thing so that we could do it. But yeah, it would be nice if you could do more than one, but then you'd sort of defeat the purpose of the low cost, easy access.
You say low cost, how much does it cost and how does that compare to a more traditional satellite?
The way it works is that we were given a grant and we essentially paid for what you call just a single string. Most satellites have a prime and a redundant string, so they essentially have backup if something goes wrong. This satellite is lower cost because it just has a prime string of sort of proven equipment, and then we put our development on the secondary string. Generally, the grant that was released for the single string was 3.5 million. It's really very difficult to cost a satellite because they're varying different requirements, but sort of standard imaging satellites can be anything between 5 and 10 million as a sort of wet-fingered guess, if you like, so it is a lot cheaper.
So for less money, you're testing more technology from a broader range of types of people and types of industries. What sorts of technology are you actually testing with Tech Demo Set 1?
We've got a range of technology, so we've got a number of radiation monitors, which are obviously of interest to the academic community. We've got a deorbiting sail, which is of vast amount of interest for everyone. We're all aware of the space junk sort of issue, so we've got a sail on board that will help us deorbit safely and sort of remove some of that problem. We've also got some new technology associated with the CubeSat community, and obviously we know they're the way forward, and a lot of people are investing a lot of time into those. So to prove some of the things that they need, there's some CubeSat technology on board. There's also a spectrometer on board, and there's tentative sort of technology to do with ESAR, the NOVASAR program coming up forward, so sort of monitoring ocean roughness and sea state, etc. So there is a wide range of technology on board.
And what benefit do you get as, satellite technologies? Surely you're just paying some of the overheads to test other people's equipment.
It is other people's equipment that are on board, but as I said, the way that it works in our interest is we've guaranteed the primary string. In response, we've been allowed to fly our development on the secondary string. So we've got our own investment in on the secondary string that we're flying, and if it works, that obviously then gives us the heritage and the in-flight testing, if you like, that we need.
And what is it that you're hoping to test on?
We've got a number of new developments. So we've got changes to the propulsion system. We've had a look at power system. We're trying new techniques for laying down solar cells. There's new data recorders on there. There's increased capability in sort of the RF area. So there really is a vast array of new technology that we've got.
And do you think this sort of democratic vision of space exploration is likely to be the way that things have to move in the future?
I think if we can prove that the industry can work together, we all know that space is a very costly industry, and I think if everyone can pull together and collaborate, it's certainly a very good way forward for the future.
Victoria O'Donovan, sorry, satellite technology in the future. Space debris is becoming a problem. Orbit is fast becoming a dangerous place to be, simply because of the number of bits of junk that's up there with you. And it's not just the big objects like decommissioned satellites that you need to worry about. Due to their velocity, even tiny particles like chips of paint can do a great deal of damage if they hit sensitive equipment. To try to prevent collisions or conjunctions, space agencies are tracking the bigger objects and monitoring the rest through various sampling methods such as regular photographic surveys of satellite surfaces. Assessing how much of a priority space debris will become relies on having good modelling, and Southampton University's Dr. Hugh Lewis addressed the conference to discuss how we got into this situation.
The reason we have so many objects in orbit is because we put them there. Our launch activity is essentially contributed to the space debris environment. And back in the 70s, 80s, we were conducting quite a few space launches. So the launch rate at the moment is actually quite a long way down compared to that period in history. But still, we're looking at 6 million kilograms of mass on orbit that we place there. And that mass is distributed in many thousands of objects and fragments. And it's the fragments really that we're concerned about. So while we've been conducting space launches, we've been having accidents in space as well. So a lot of our the upper stages have gone up, some spacecraft as well have been involved in fragmentation events, so possible explosions and so on. And that is continuing. So even in October, we saw the explosion of an upper stage. And each of one of those events is going to be adding hundreds to thousands of new fragments into the environment. So really what we want to try and do is to stop that from happening. And a lot of the mitigation efforts that we've got are focused on passivating those upper stages so that there's no more residual propellant on board to produce these explosions. But then we have to shift our attention to the collisions that have already occurred and the ones that we are expecting to occur in the future, and do our best to minimise those.
So we've littered our own space environment, but now the objects already up there are making the problem worse by colliding and breaking up into ever more smaller objects. Depending on their height above the Earth, these can persist for many years.
When these explosions and when these collisions are happening at higher altitudes, the fragments that are produced stay up there for longer. When they're lower down, the lifetimes are much shorter. And in fact, around about 800 to 1,000 kilometres, we're looking at lifetimes of decades to centuries for some of these objects. And that is pretty much where the two worst events have taken place, which is the Chinese satellite test and the collision between Iridium and Cosmos satellites. And those fragments are going to be up there for a long time, and they contribute to the conjunctions that you see, ESA certainly is seeing with respect to their spacecraft. Probably about 50% of all the conjunctions that they monitor involve fragments from those two events.
Computational models allow us to investigate quite how persistent these objects may be and how much of a problem they're likely to become.
So this software, which we like to call Leverage, enables us to try out lots of different scenarios. So we can experiment with lots of different mitigation options, we can experiment with debris removal, and then we can run the simulation forwards for a couple of centuries to see what benefits, if any, we see.
The damage model can be used to map active satellites and then superimpose on top the locations of any debris that's bigger than 10 centimetres.
When you superimpose the actual 10 centimetre environment on that, so this is actually data from European Space Agency's master model, you start to appreciate the problem that we've got 1,000 active satellites, but here nearly 30,000 objects that we can currently track. So the active population is actually a very small percentage of the orbiting population. And really that's where the problem lies. We can perform collision avoidance manoeuvres with our active satellites, but they account for such a small fraction of the on-orbit population that there will continue to be collisions in the future that we cannot prevent, unless we start to go up and remove the objects that actually exist on orbit. Now, with respect to our damage model, what we can do is we can start off with this population and we can run forwards 200 years. And if we don't do anything, the number of objects is a trackable population. To get to that point, we estimate about 100 catastrophic collisions, of which only a tiny fraction would have involved the active satellites. So we have to try and prevent the collisions between the defunct satellites, the spent upper stages that are on orbit at the moment and will be placed there in the future.
But reducing this number is likely to present many challenges.
There are a number of debris mitigation guidelines, and there's one in particular which is highly effective in terms of reducing the number of collisions that you would see in the future, and that is to limit the lifetime of objects in low Earth orbit after the end of their mission. Sometimes referred to the 25-year rule. This can have a dramatic effect on the future environment. If we just implement that 25-year rule, so at the end of your mission, you the purity of the spacecraft or the upper stage, so that it enters the Earth's atmosphere within 25 years, we see tremendous benefits. But it might not be enough. The current population is sufficient for these collisions to continue into the future. So as I've already mentioned, most of the population that we see, the trackable population, spend satellites, they're fragments. So there's nothing we can do from down here to change their experience with the collisions. So we're now really contemplating, I guess, a new future which is going beyond the debris mitigation. Mitigation is aimed at the generation of new fragments and new debris. Now we're talking about actually going up there and getting rid of objects that are already there that can't perform these collision points maneuvers. And it's active debris movement. I think at the last ESA conference on space debris, this was highlighted as the #1 topic in the space debris area. Active debris. And there's a tremendous amount of activity in this across Europe and actually internationally as well.
There are many ideas for how we should go about removing debris from orbit, from giant nets through to space harpoons and the use of lasers to slow and therefore lower the orbit of different objects. All of these have pros and cons, so the discussion is far from settled.
What I'm interested in reading is what happens if we do this? What happens if we start to remove the objects? And what questions there are. So the technology is one issue, but we've also got a question. If we're going up to remove spacecraft, then what's the purpose? What's the goal? And identifying that goal is going to be really important in terms of the technology that we need. So that's one of the key questions that we've got, but there are others as well. And one of them, the question really that's important is if we don't remove them all, and it wouldn't be very expensive if we tried to remove them all, then which objects do we choose to remove? So what we've done at Stanton is use the damage debris model really to see where the collisions are actually occurring. And we can identify a number of different clusters. And the key ones are the sun synchronous orbits. There we have a variety of different kinds of spacecraft and upper stages. And the other one is slightly lower in terms of the orbital inclination. These are essentially on retrograde orbits with respect to the sun synchronous orbit. So they're travelling very quickly relative to those spacecraft on the sun synchronous orbits. And they're mainly upper stages. So we've got a kind of a variety of objects. But if we can go in there and you can say, well, those are the ones that are more likely to be involved in collisions in the future, then those are the objects that we want to be targeting and removing from the environment. And that's precisely what we do in terms of our simulation, simulate that process. And what we find is, even if we select in those regions, it doesn't really matter which of those clusters that we target, as long as we target those clusters. And we find that we see some benefit.
We have potential technologies, and our models are telling us where to go to remove the debris, but removing enough might be too expensive.
It's not as if you're removing one spacecraft and not into one collision. Because we don't know that the object is actually going to be involved in a collision, it's essentially something else, then we have to remove more than we really want to avoid one collision. And it turns out we have to remove about 50 objects to prevent one collision from a statistical point of view. And in our studies, we find that we can achieve this if we remove anywhere between 3 and 10 objects per year. Now, just to translate that into, I guess, financial terms, so just in the 50-year period we did that, it's 150 to 500 removals that we'd have to perform. If we assume that each removal is essentially one new spacecraft that goes up to remove another object, $300 million per removal spacecraft, then you're looking at $1 to $3 billion per year. It's hugely expensive. So, but somehow we need to be able to kind of say, well, the object is going to be involved in a collision, so if we remove it, we've prevented one collision from occurring. That would be the ideal scenario, and that's what we're going to try and work towards. Whether it's possible or not, I don't know.
The problem is far from solved, and Dr. Lewis argues that we need to get over 4 new problems before we can start to clean up our space environment. They are consensus, cooperation, collaboration, and contributions.
There are 4 other challenges that we need to address, and these kind of encompass the technical, the financial, the political, and legal issues. Consensus: do we actually need active debris removal? Can we get away with existing mitigation guidelines and so on? Cooperation: some of the debris targets will belong to one particular country, and the removal operation may be performed by another. So some cooperation is required, but certainly from a legal and a political point of view. Also, we'll need to collaborate. This will need to be an international effort, and certainly this is something that is highlighted in the US space policy. Contributions: this is very, very expensive, as I've already tried to indicate. So somehow we need to share the cost. Somehow we need to find the money to perform these kind of removal operations before we can contemplate a campaign to remove these objects.
Dr. Hugh Lewis from Southampton University. Finally, the Low Frequency Array, or LOFAR, is a radio telescope that's working at the lowest frequencies accessible from Earth. It features stations scattered across Europe, and it started its official science program this month. To find out more, I spoke to Derek Mackay-Bukowski, station manager at the LOFAR station at Chilbolton.
I think probably the most exciting thing about LOFAR is that it's opening up a huge new parameter space in the scientific observation field. And if you consider that we have looked at low frequencies before, but it's never been with high time resolution, we've never looked at it with high sensitivity, so it's something that we glossed over 60 years ago when radio astronomy first got started, and it's been neglected ever since. And since then, we've effectively accumulated 60 years of technological advances, and only now, for the first time, are we going back to look at what was the cream of the science back then, but with all these new resources available to us, and LOFAR makes use of all of them, in terms of high sensitivity, high time resolution, high spatial resolution, a lot.
will we be looking for? What is this low-frequency radiation useful for seeing?
There's no single answer to that. I mean, the problem is that at these low frequencies, there's lots of different physical effects that you can see at different distances away from us. Some of them are in our atmosphere, some of them are within the solar system, and others are effectively at the edge of the universe. One of the most interesting cosmological programs on this is the epoch of reionization. This is the moment after the Big Bang, everything's ionized, the universe then cools down, and eventually you get clumping, and stars start to form again. And only when those stars ignite do you start to see this reionization effect. And LOFAR, because of the frequency shifts, because it's a low frequency, it's perfectly placed to be able to make that connection. Just an incredibly important cosmological result that we'll nail it.
Now, when I think of telescopes, and in particular radio telescopes, I think of big dishes, usually on their own, but occasionally in twos or threes. LOFAR is an entirely different philosophy of observation.
Exactly, it's a completely different concept. It's what we call a phased array. So we have not just a single dish, but we actually have an array of antennas. They're distributed over a huge area, and as the case may be, it's over 1,300 kilometers of extent across north and western Europe. The individual stations themselves are made with lots and lots and lots of antennas, rather than just a single dish, and the parts themselves don't move. So what we use instead is we use an electrical technique to change the direction in which these antennas are sensitive. So in other words, change the direction in which they're pointing.
How does that actually work? How can you steer a telescope that doesn't move?
This is really difficult to explain using just audio. However, okay, let me give it a shot. The way that it works is that if you have a wavefront, radio waves coming in from space, okay, if they're coming in from directly overhead, they will reach all the antennas at the same time. In other words, if they go through the same length of cable at the same time, they will arrive at the detector at the same time. If they're coming in from a different direction, if they're coming in from the horizon, they'll arrive at one side of the array before they arrive at the other. So in other words, when the signals go through all those cables, they don't come in lined up together. They're all out of sync. They don't add together, so therefore that particular telescope is sensitive to what's directly overhead, but not sensitive to what's on the horizon. Now, you can change that by delaying the signal as it arrives. So signals arrive, just delay it for a little bit, store it in RAM, store it in computer memory, and wait for a little bit. And then, only when the rest of the signals are caught up, then let it go through with the rest of the system, and so therefore you do get an addition, and you do end up getting a strong signal. And so by using this digital steering technique, we can actually change the direction in which that array is sensitive on the sky. But of course it's digital, so therefore you can make as many copies as you want. So if you want to make a second copy, adjust the delays in a different way, then you're sensitive to a different direction of the sky. So not only can we go from one side of the sky to the other very quickly, we can actually look in more than one direction at once.
And is this also what enables you to have such a huge geographic divide? Because obviously if you've got one set of telescopes in France and another one here in England, then there's going to be a huge delay between the two.
Oh, that's correct, yes. And so therefore you need... Oh, that's correct, yes. And so therefore you need extremely good timing between your stations. You need to make sure that you can timestamp the data that is being taken. We then pass it across commercial networks, which there can be all different levels of lag and latency as it goes across Europe. But when it does get to the correlation point, then you can look at those timestamps, you can work out where the data lines up, and you can put it back together again.
So that gives an opportunity for cooperation as well. Presumably there will be scientists throughout Europe using the same data from the same array of telescopes, but using it in slightly different ways and getting a wider array of scientific answers.
Absolutely.
Hello to those watching on Kick, but also hello to those on Twitch and YouTube as well.
But at a scientific level, we find that the data that we're taking from some experiments is perfectly valid for more than one research question. So therefore, we can use some of the data for imaging, and at the same time, we can use it for looking at radio transients. At the same time, we can use it for looking at ionospheric research. A whole host of different applications. But again, this is something that is made possible by the fact that we've got digital information that is easy to copy and manipulate.
There's been a lot of excitement about the square kilometre array, which uses the same sorts of technology. How has LOFAR sort of paved the way for this?
Well, LOFAR's been very influential for the SKA. One of the big questions that was facing the SKA in its early stages was whether or not it was feasible to use this technology for it. And LOFAR has demonstrated that that certainly is the case for low frequencies. If you look at the current design concept for the SKA, you'll see that the SKA actually uses a hybrid of both dishes and phased arrays. And so phased array technology started with the SKA has extremely heavily influenced by LOFAR.
The SKA has still got a few years before it's active, but does this mean that LOFAR will therefore come to a date by the time it switches on? Will it become redundant?
Well, apart from the issue that the SKA is going to be many years yet before it's fully operational, it's a complementary instrument to LOFAR in several ways. Firstly, LOFAR operates at actually lower frequencies than what the bottom frequency of the SKA is. Additionally, LOFAR is located in a different hemisphere, so therefore, while the SKA is looking at the southern sky, the Magellanic Clouds, the galactic center, LOFAR is looking off to the northern sky. So therefore, they're complementary instruments to a certain extent. And of course, there is also the issue that LOFAR is also geared up to do a number of these ancillary projects related to agriculture, geology, ionospheric research, atmospherics, etc.
Speaking of which, LOFAR has just switched on very, very recently, so we should expect to see data coming in very soon, scientific results very soon. What do you think we should be looking out for in the headlines?
Yeah, well, this is true. I mean, LOFAR started its formal scientific operation last Monday, so it's only a few days ago now. But already from the commissioning phase alone, we've seen some pretty major papers coming out regarding pulsars, regarding cosmic ray transients, and regarding extremely deep radio imaging. So I think that over the course of the next 6 months, we can probably expect some really exciting results coming through. I think pulsars will certainly be one to watch. The epoch of reionization is another one that everyone is keenly watching. And I think there's also a great possibility for serendipity here. I think that LOFAR, because it is hitting a relatively unexplored region of the electromagnetic spectrum with so much power and sensitivity, I'm sure that we'll be uncovering a lot of things that we just did not anticipate.
Derek Bukowski from the Radford Appleton Laboratories, station manager of the station, Short Bolton. That's all we have for this month, but as always, you can find more on our website at thenakedscientist.com/astronomy. Naked Astronomy is produced by Dominic Ford and me, Ben Valsler, and comes to Cambridge University with support from the Science and Technology Facilities Council.
Supported by the STFC. This is Naked Astronomy. For more information, look us up online at nakedscientist.com/astronomy.
Managing global finances shouldn't make...
From professionally designed or DIY investment.
Tens of galaxies, there are millions of...
It sounds very similar to the CubeSat idea, which is where you have an entirely different philosophy of observation, isn't it?
The direction in which these antennas are sensitive around. So a very different body of operational ancillary projects regarding activity. I'm sure
STFC. This is
Ben Valsler and comes to you from Cambridge University with support from the Science and Technology.
In local currencies and save on FX fees. Simplify your workflow with automated admin. Get full visibility and control to keep your cash flow strong. The financial platform for your local business needs all in one place. Visit ofx.com. Visit the PDS and TMB online.
I'm calorie counting.
I'm doing checks.
I'm doing health.
Hot fasting.
Yeah, keto. They can do it the hard way. I'm doing blind basing. It's perfectly portioned meals so I can lose weight without losing the joy of eating. Stop losing weight. The love easy way.
The problem was that easy to figure out what was the root cause of this chaos.
Our studio guests are the anaesthetist, Wellcome Trust Public Engagement Fellow, and expert in the effects of long-duration spaceflight, Dr. Kevin Fogg from University College London, and our Space Muffins regular, Space Kate Artless-Gray, will be looking forward to an exciting year ahead in space exploration.
Kevin, before we get going, I read in one of the interviews I wanted to be an astronaut since the Apollo-Soyuz missions of the mid-70s. Now, we're almost 40 years on. Is it looking any more likely?
Yeah, I'm not entirely sure. Got a quite fulfill that professional ambition. I was in the European Constitution in 2009, and sadly I made it to a few rounds, but not through the final round. And that's a lot of money and get someone to...
So you're prepared to pay it?
Yeah.
Speaking of being prepared to do anything to get into space, Kate, well, I know, I mean that in a nice, clear, kindly way. We've documented, haven't we, you in previous podcasts, how you've really made an impact in getting closer and closer to your dream. Do you think you'll be any closer to it in 2013?
I don't know. I've actually just caught news of a competition that's being run this year to send 22 people worldwide to these orbital flights. So one person from the UK might get to go. So I think that might be my new thing for this year.
You probably shouldn't tell anyone that, though, should you?
No, I didn't mention the competition. It's okay.
Okay, fine. Now, living in space can seriously damage your health. Don't take my word for it. Here's Shamila Bhattacharya, who I met recently at NASA's Ames Research Center in Silicon Valley, California.
Reduction in bone density, there's a loss of muscle, vision can be affected. So there's a variety of different effects that can happen.
And all these effects that you talk about, they're all caused by being in a zero gravity or microgravity environment.
No, that's not the whole thing. Some of the effects we think are also caused by radiation. Now, so far, the shuttle and the International Space Station is at a somewhat more benign radiation level-wise benign environment. However, when we go outside of the exposure to the atmosphere, we will be exposed to more radiation. And so, in addition to microgravity, there's also the effect of this ionizing radiation that will impact the organisms' existence. Also, would like to understand better.
Now, you've got one of your experiments on the moon. These are small boxes around the size, I suppose, of a large matchbox, and they're crawling inside with fruit flies.
Yes, exactly. So this was an experiment that we spoke 2 years ago, and we were interested in looking at the changes of the immune system. So we wanted to use the fruit fly model, whose innate immune system is very, very well characterized at the molecular level. And what we did is we sent up a cohort of flies to space, and then we actually had the analogous set, so their sibling, if you will, an identical batch, on the ground, treated exactly the same, except for the animal. And then we compared, after spaceflight, when we got the flies back, we compared a variety of different measures of immune system changes between spaceflight and ground.
And what did you find?
Yes, it was very exciting because we found that there were distinct differences between the space zone animals and the ground zone animals. We found there was a reduction in the function of the blood cells in terms of how well they were able to phagocytose. Phagocytosis is a process whereby the blood cell can induce invading microorganisms to protect the body against an infection. And we found that there was a reduction in efficiency in that process from the space zone animals. We found also that there was a reduction of blood cell numbers. We found that there was also a change in the expression of genes and molecular biological changes that we measured from the animals from space.
Does this mean that humans leaving the Earth into deep space away from the low Earth orbit are going to face this as a serious problem, that they're going to be more susceptible to disease?
They may well be, yes.
Shamila Bhattacharya from NASA Ames with her fruit flies. Shamila listed quite an alarming list there of things that can go wrong. How worrying is that list if we're genuinely considering manned missions to the moon and Mars?
When it comes to human missions to And when it comes to mission design, adding people into the equation, wrapping systems of life support around them, and then projecting them across that void, and hoping they stay healthy, it changes the problem by an order of magnitude at least, I think. So we do need to worry, and that experiment there was talking only about the immune system, which is only really beginning to understand in space.
I must admit, that's the first time I've heard about effects on the immune system. Can that be sort of accurately transposed from food supplies to human beings? Have there been experiments on astronauts on their immune systems?
So it's interesting because we've done animal models in other areas between animals and people in space. So in rats, for example, is not the same in rats as it is in humans. So the amount that you can extrapolate directly is limited. However, what was really interesting about her experiment is that they knew that astronauts became immunosuppressed, but they said, well, look, there's lots of things that immunosuppress you that may not be unique to space environment. So if you're really stressed, like say you're going around the Earth at 70,000 miles an hour, which is away, trying to get a multi-billion-dollar mission done and not fail, those things might stress you out and immunocompromise you without having to be in space at all. But that experiment, what it elegantly demonstrates is that actually, if your flies, you probably don't know you've gone into space, and you absolutely control very carefully the ground population against the guys who are flying, you still see those things. So there is probably something specific to the space environment that impairs your immune system.
Does this perhaps give more weight to the prospect of one-way trips to, say, Mars, rather than there and back, because they're not halving the sort of potential effects on the human body?
There are so many other problems on top of that. You know, your muscles start to bones, like your heart, which itself is a muscle, begins to diminish, your blood vessels get floppy, your hand-eye coordination gets shot, and I can go on and on and on. And that is all if everything goes right. You know, that's before you start to think about what happens if you have to do some first aid in space or then it's really easy. And so with all of that, because those problems are so familiar,
that hurts. It's surprising. That doesn't feel like it would hurt, but it does. It's getting those little muscles, those little muscles around your hips. I mean, that's what the target is, isn't it?
It came up during the lunar missions as well. So I think people will talk about it. I think it's an interesting academic exercise. I'm not sure that we will ever do that as a profession.
Okay, I was just wondering, I'm sure there's been some experiments done in space that have found that viruses...
This is my last set.
So if you couple that with your immune system being...
Last set for leg day.
You might really have a big problem. So what kind of angle would you take? Trying to control the number of viruses on station, or doing something to make your immune system stronger?
So that is true, actually. There is a well-characterised increase in virulence of the viruses when you send them to space, and then there's a weird thing that happens that the genes of the virus get upregulated to make it, some of them at least, more harmful. And yes, the big worry is that coupled with impairment immunity is a sort of massive risk. And there is no short answer to it, because no one's been out there for this reason. They're just about to kick off some truly long-duration space station missions of over a year's duration to try and start progress some of the longer-term issues, but it's going to be hard.
But even then, with those long-duration space station missions, as Shimona was saying, they're within the Earth's magnetic bubble, the magnetosphere. You go beyond that missions, long-duration mission to the moon and certainly to Mars. You're just bombarding all this stuff from the sun as well.
Yes, and most of my area, the stuff that I've looked at has been about effects of the absence of gravitational loading, and in fact, most of the research I did when I was at NASA looked at the artificial gravity pilots that have to spin astronauts to try and combat with gravity. But then, of course, you are with this huge problem of radiation. And
that's it for today.
That's
for today's workout.
Flux of particles that comes from the sun during solar flares. And there's not a good answer to that at the moment. That stuff cuts straight through your vehicle and you and strips out your bone marrow and every other reptile cell population. And if you are in space and you get a solar flare going off, it is like standing next to a neutron.
Alrighty, that's it for today. Thank you for watching. Thank you for commenting. Any questions, put them down in the comments below and I'll try and reply, I guess. Alrighty. Good night for now.